Hi, welcome to the introduction video to PID control. We have started a little bit in class to do PID control, and we continue and carry this further. So to remind you, this is the basic of our control system. We call this feedback control, and remember we do negative feedback. So we have a minus here. We're comparing the process variable and the reference point. So we have defined our process. We've described it with our transfer function g of s. That's our process dynamic. And it reflects the dynamic behavior of the process in the long term, in the steady state, as well as the short-term dynamics. Now we have to choose a good value for our controller, C of S. And the simplest choice is to choose this as a proportional value. We call it a proportional controller because it is simply a constant K. So we're choosing C of S equals to K. There is no dynamics in there. It's just a one-off factor. And it means that we have our controller output U is equal to this parameter K times our current error signal. So the controller output of T is our error signal of T times the controller gain. We call this K is the controller gain. Controller gain. Now, we have to modify this in the time domain slightly because we don't want the controller gain to be 0 if E is equals, so the controller output to be 0 if E is equals to 0. So if there has no error, we would probably like our valve to be 50% open, maybe 70% open. So this U0 is the controller output if E is 0. Okay, and we have to fix this. So that's a problem. Because as a result of the dynamics, we get an offset if we apply only P control, and we showed that this offset is equal to 1 over K plus 1 or 1 plus K. And if we do the proportional control alone, we get the following. I do apologize for the squeaking. Use another pen in a second. So if this is our process variable y, and this is y, this is u, we are closing the loop. We have a proportional controller. That means if we have a set point change, or if we have a, let's rather do disturbance rejection. So that means our reference point R is not changing. At a point in time, T equals to 0, here, a disturbance will hit our process. We don't necessarily see that, but what's going to happen is we have an offset. This is the offset for for set point changes. We're having a disturbance rejection here, and this shows that the disturbance hits us, but the proportional controller is unable to steer the process back to the desired set point. And the reason for that is that we're adjusting the controller output, but not as much as we should. So we have an adjustment in the controller output, but it would need to be more in order to counteract for the disturbance. So if we write this slightly differently, we can write it for E. We solve it for E by putting U0 onto the other side. E is U minus U0 divided by K. Okay, and we would like this error to be 0, and that is only possible if U goes to U0. But that's not true, because we have defined once for our controller. This is maybe 50%. Yeah? So this is why we are getting this remaining controller error here. This is the remaining controller error E offset. Okay. So now we had someone had this very extremely brainy idea. So let me just draw that. That's like someone had this super, I don't know who, like someone in the past, was not recorded who that was, had this super brainy idea of removing the offset by introducing an integral action term. So we're removing the offset by setting U0 proportional to the integral E of t dt. Okay. Because then there will always be a control action unless E of t equals to 0. I'll show you that in a minute. In the meantime, I want to summarize the control law. This is what we call the control law. And that is for a PI controller. So we can call this UPI, for example. And that is K times E plus the integral E of t, missed something here, Ki integral E of t dt. Okay. Now we have to make a relationship. We have to find a relationship between K and Ki. And normally we define this parameter as 1 over Ti integral E of t dt. Okay, so that Ki equals to K divided by Ti. Okay. So let me show you what that effectively means. It means that if we have a control error over time, not having luck with this pen. Let me try a different one. I've promised myself not to try out different pens, but now here I am stuck again. So imagine this is your control error, and for a bit it's positive and then it turns negative, but there's a remaining control error. And if I look at time t, so this one here is time, this is time t equals to t, I have to, in order to form the integral, this bit here is the area under the curve. This one here is positive, and this area here is negative. So now this area is proportional to the integral part, and this is our integral action. So this, everything here in yellow is the I part of the PID controller. Okay. So if we consider the control error, the P controller, the P part says K times E of t is constant if I have this constant control error, This is the little bit here. But the benefit is that the I part looks as follows. That the integral of e of t dt will always increase if e, this constant here, is positive. In this case, it's negative. So it will always decrease so long until I have no control error. So the I part makes sure that we don't stop with the control just because we are stuck here at this level here. Okay. If e of t doesn't equal to 0. Okay. So it's going to increase, so the control action will make sure that our control error will increase on or decrease. Here it's going to the error will increase. It's going to change until we have no more error, until e of t is 0, becomes 0. And this is by definition the case. Okay. So what does the disturbance rejection now look like if we have a PI controller? So the pink part here, this here is a P-only controller. The yellow bit here is our PI controller. And what's going to happen is it's going to make sure that we're getting a decrease. So we're going to see the disturbance. It's going to be present for us for a certain amount of time, but then it's going to decrease. And what the result is for the control action is that here we are going to add more control action in the long run. So it's going to take a little bit, but then eventually we will compensate for the disturbance. So the integral action removes the offset. Okay. All right, so this is our control term. So now if we want to see this in the Laplace domain, we're going to take this equation here and we're going to Laplace transform it. And then we're getting u of s equals to k, open bracket, e of s. This is the point where I need to pull my chair in and write it like this, plus 1 over ti. So now, what is the Laplace transform of an integration? You can look it up in your lookup table, and you will find it is 1 over s times the function. Or you can think about it by having a function dx over dt equals to y. So if you do the integral on either side, you're getting x equals to integral of y. If you do the Laplace transform, you will get s times x equals to y. So you can also know that the Laplace transform of a differential is equal to the modification with s, multiplication with s. And then you use it, you solve it for the other side, and you know it's 1 over s. So the integration is the reverse of the differentiation, so it's 1 over s. Okay, we can write this slightly differently. We can factor out e of s, and we end up with 1 plus 1 over tis e of s. And if we want the controller function c of s, this is u of s divided by e of s, and this is k. And in our transfer function, we would like to know what are the poles and the zeros. So what do we have to do? We have to expand the 1 here with ti of s divided by ti of s. So we have tis plus 1 divided by tis. So that's our transfer function of our pi. That's a pi controller. So we could call this here CPI of s. Okay. Now, to sum up, there is no fundamental difference here. There's no fundamental problem here with this disturbance rejection. we can reject the disturbance. We may not do it at an optimal way, but there's no fundamental problem. However, we can improve it. So first of all, so just to say that again, most processes in the process industries can be controlled and are controlled with PI controllers. So think about it here as quite a big break. So we're taking a stop here, yeah, and we will say this is okay. This is enough for now. Or we can have we can carry on, and now I'm just thinking what color I'm going to use, because now we can extend it with the derivative action. So I would like to use blue because that pen is very strong, but I don't want you to confuse it with the reference signal. I don't have many other options. So let's use blue and try not to get confused with the reference signal, which you're not going to do. So this is the I part. Now we're coming to the D part of the PID controller. And it goes like that. Or, well, the motivation to use the derivative is the following picture. Think about two control scenarios. You have E of t as a function of time. So this is our error signal as a function of time. So we are starting off here, and we move along. Yeah? And we're looking here. This is again function time. At this point in time, we have considered the integral here. Now, consider a second scenario where we're having a control function and something happens here right towards the end. So we're now here at time point t. Our integral looks like this, and our current value is in the same order as in both cases. So these scenarios look identical for a PI controller, because the PI controller looks at the current value, the present value p, which is here, which is very similar to this present value. So that looks similar. The integral is also looks the same. However, if we see this error signal, we're seeing, oh, here, our error is going down. And I'm drawing this as an arrow pointing downwards. In this instance, our controller error is pointing with an arrow pointing upwards. Okay, so if you were a human, you would say, oh no, I have to react very differently, because I have to make sure I'm counteracting this upward trend, and I have to insert more control action. Whereas in this instance, I know, okay, I can relax quite a bit because our error is going down. Yeah, so I just back off a bit. Don't do as much control. Okay, so this part here is D. So again, to recap, P is the present value. I is the integral, that's the past. And D is looking, where am I heading, in what direction am I going, and that is the future. Okay. So now we capture this D by looking at the derivative, dE divided by dt. And we factor this into our control function, and our control function is going to look like that, of a PID controller. It is U equals to K times E plus 1 over Ti, our integral part, plus another factor Td, dE over dt. Okay. So this last bit here is our derivative action multiplied by K. We call Ti, I should have said this at this point here, but let's write it down here. Ti is the integral time, or we also call this in English the reset time. In German we call it Nachstellzeit. Td is the derivative time. In German it's the Vorhaltzeit. Td, the size of Td expresses how far ahead we are looking into the future. So we're looking, is this really going very fast? So it's an indication of how confident we are in our prediction and also how far ahead we are predicting. Okay. You have to be with a D part. Many people don't use the the D part. And the reason for that is that you have to be careful is your signal is noisy. You can imagine that. If your signal is noisy, it goes up and down. So you're going, 1 second you're going, I'm going up, I'm going down, I'm going up, I'm going down. So you're going to get very confused, and that is not a good control law. This is not a good control strategy. Okay, so you have to do a simple trick, and that is you have to filter the signal. So you have to apply a low pass filter so you're getting the trend. Where am I heading? I am heading downwards, upwards, and don't be confused with the wriggly jiggly behavior of some additive noise that you may get. Okay. The D part, so be careful with noise. If Y is noisy. Yeah, so if it looks, something happens, there's like a big up and down here happening. So in the whole trend, the overall trend is clear distinction, but we have this wriggly jiggly behavior. What I also want to tell you is that the D part works best if you have higher order processes. I'm writing down as HOP, higher order processes. In German we call them PID Introduction. And for those, the step response looks something like this. So this is the model step response. This is the open loop response. It will look for something like this. And for those processes, we get a very good behavior for if we're introducing a D part to control that kind of process. Okay. Let me indicate. I'm trying to do this in blue. Think about it as a different color. So what is it going to look like? The pink one was P. This green one here is the PI controller. And now I'm going to draw in the PID controller. And that's going to look even better than this. It may have a small undershoot, and then it's going to return to the set one quicker. So that is normally what we like better in a control action. On the other hand, this signal here is going to be more control action, and then it's going to come back to the same signal. Okay. So a good way of thinking about PID control, and particularly the D part, think about a temperature process where you do this intuitively. Think about you're cooking, frying an egg, or if you're frying some steak in a thick-based pan. If you have a disturbance from the outside, something happens, you put in another steak and the temperature will cool down. In order to make sure that the temperature stays at a constant level, you will do action immediately. So you're going to do something predictive because you know the effect will take a while, because the time from increasing the heat of the stove until it actually increases the heat in the pan will take a long time. And reversely also, if you want to decrease the temperature, you're going to do this well in advance, and you're going to do it probably more than you have to, than you would think you would have to, because it takes such a long time for the temperature to go down. So this is exactly what you're going to do here. So you're increasing, if you want to increase the temperature here, you're going up, or you're dealing with an increase in the disturbance, you're going up and you're compensating for it. Okay, and that is your P, I, and D controller.